Hi, all you lovely creative aviation enthusiasts out there. So this is the continuation of the Levitator project, and quite frankly I do not really know where to start to describe this machine. This video might be a one-off video. It might just crash within the first seconds of flight and then it's over. So be prepared for that. But I'm hoping for that this is the first video in a longer series of videos covering the characteristics and the nitty-gritty details of this machines in upcoming videos. Okay, so this is my attempt to harness the positive characteristics of the original Levitator, which was a slow-turning, large wing area rotor wing vehicle. And the positive characteristics I'm trying to maintain here is the hover efficiency and the relative simplicity of the build, especially the wing structures, and the redundant and fail-safe nature of this kind of vehicle, which has a tip-mounted propeller on each rotor blade, and also the relative low sound profile, especially when you are in the center of the vehicle or standing underneath it in the model scale, and in the dream vision scale when you're sitting in it, you are far away from the propulsion units. And the negative characteristics I'm trying to mitigate with this counter-rotating design is of course the dissymmetry of lift problem, which becomes so acute when you have a large, slow-turning rotary wing flying machine, where the retreating wing will stall even in a gentle breeze, or when you are traveling at relatively or actually very slow forward speed. It could be like 10, 15, 20, 25 kilometers an hour, and you are just hitting the wall with the retreating blade stall, which makes the machine flap back and hinder further acceleration forward. So to be able to stack two Levitators on top of each other, it was necessary to leave the wire braced structure, and I really didn't want to leave that setup because it was so weight saving for me to use wire braced wings. So here I have these two tube struts, those underneath there. And they don't support the wing at all in the same way as the wire bracing, where the wires went almost out to the wingtips. So I need significantly beefier wing tubes on the wings to make it possible to carry all the loads through a single point there underneath the wing, and the half the wing is not supported from that point on. So this gained a lot of weight, which of course will hit the hover efficiency. But this is a design compromise I was willing to try out in this composition. And just a second ago I moved around the undercarriage, so the whole setup is actually standing on a large bearing. And this is for me to be able to try out the yaw system. So I will show you a close-up picture of that later on, but it's a differential braking system, and that's one of the first tests I want to do, because that's one of the highly experimental design features of this setup. And there's also one thing that I couldn't do in my workshop, and that is the wire bracing of the rotor blades. So yeah, I have these struts underneath, but there's supposed to be a wire connecting the three wings laterally, so that they can't, so that the distance between the blades are the same. And this is of course both for just general rigidity, because otherwise I would snap off the wings at the root there where the servo is. But it's also a fail-safe design feature. So if one motor breaks, the other two motors can pull the wing with the broken motor through the air, so that you get a possibility to just keep on flying and landing it safely. So here I will do a little bit of wiggle, so you can see it's very flexible, and each blade is very flexible. So they're supposed to be interconnected, in that plane, just to enable this fail-safe feature. Yeah, there's a lot of this. I mean, this is the very first time I assemble the machine, so it's a lot of reflecting and thinking, and try to get a feel of the structure and find out various flaws. And as you saw previous, I just gave it a little bit of lift. I wanted to see how heavy it is, you know, at the moment, and the all-up weight is depressingly high, although it does carry 5 kilowatt-hour of batteries that I have reused from the chair project. So the very high all-up weight means that I have to have a way of storing it outdoors. It's too heavy to move around, and it takes a little bit of time to disassemble it, although I have designed it to be like fairly simple to disassemble. The wings are only held in place by 2 bolts each, and the interconnecting wire between the wings also has to be disconnected. But other than that, the wings are just easy to pop off. But again, it's a big machine, so it's not something you do each time there's like a rain shower coming in. So this is my weather protection thingy. So this is the first time I'm just checking out if my brain was braining when I designed this, or if my brain was out of order. But it seems good. There's a thick Velcro strap on the inside of each of these 3 like tarpaulin stripes, so they protect the electronics and the central part there pretty well, I think. And it goes all the way down covering up the flight controllers as well. And of course I will need to have some sort of anchor to the ground with some wire holding the wings in a certain position, so it doesn't windmill or like start to harm itself. So this is just one of those things you can't try out until you have assembled the machine. And as you can see, I'm still missing the lower wing there, but this is like the first step. And let's take a look I mean, if this machine actually survives the first flight, I will do a more in-depth show of each the subsystem and the construction, but I will give you just a little peek of the internal design there of the wings. So this is how it looks. It's a central wing tube there that carries most of the loads, and then there are ribs also of aluminum tubing, like I think it's 12 millimeter aluminum tubes, and the wing spar there is like 40 millimeter. And then there is a steel wire creating the outer perimeter of the wing, the trailing edge. The leading edge is actually a PVC tube meant for electrical wiring in the walls in home construction, which you can see here in the front. And the wire in the front is supporting that PVC tube via the 3D prints and the end of the aluminum tubes to create this bow in the front. And here I also added the polyethylene covering material on the I think it's the bottom part there of the wing, which is like 100 gram per square meter covering material just for outdoor use generally. Okay, and now we are assembling the lower rotor here. And you can see that I still have that rain protection hat stuck on the top there. So yeah, I realized that I could of course make these covering hats, one for the lower and one for the upper rotor. You can make them separately and make them more of a permanent part of the structure, because it's very lightweight, so it could actually be a part of the flying structure, so that I don't have to worry so much each time it comes a little bit of rain or other sort of like downfall. So here I'm about to put in the lower bolt in the in that last wing there, and it acts like a hinge. So once I put that in, I can just flip up the wing, and yeah, I have to align it first to make the sprint go in, the bolt go in. But then I can just flip it up with the lower bolt there as a sort of a hinge line, and then put in the upper pin there. So it's fairly convenient to to assemble it. But this is, I mean, the model scale, so I can almost, the lower one I can just handle by myself, but the upper ones I need the leather to do that, and of course the support there at the end of the wings so that I can fiddle around with the bolt at the inner part there. But the bigger version, if I made this like twice or 3 times the size, I would need some sort of little built-in crane in the top of the structure to winch up the wings, I think. But it's all good fun to solve that kind of problems later on. But for now, it looks like this. So moving around the camera now, just to give you a little better feel for the structure. And let's take a look at the massive amount of batteries. There are 72 battery packs, 5.2 amp hour, 4 cells each. So that's just about 5 kilowatt hours of battery capacity. You can see the wire there on the upper rotor interconnecting the wings, and the lower rotor does not have that wire yet. So that's next up to cut that wire to length and fasten it. So I did that, and then the next step is to mount the wingtip propellers. I only mounted 1 propeller on each rotor. For the first yaw tests of the differential braking system, I only need to be able to spin the rotors in opposite direction to find out if I have enough control over the yaw with this braking system. So the wingtip speed out there will be just about around 100 kilometers an hour. A little bit more if you have a heavier payload, or less if I'm flying it just as a radio control model without any payload. So I think I would optimally need somewhere around a 24 by 24 inch propeller for this job. And I did order one of those just to check it out, and it's from Fiala, and they are like really good looking. But for now I can't afford to buy 6 of them, because believe it or not, this project is actually on the budget, and those 72 cells, as I just mentioned, are recycled from the chair project. So they have actually been sitting on the shelf for many years now, so it will be interesting to see how they hold up. So I bought 6 cheap ordinary like hexacopter, just multi-rotor propellers, and cut them off. So these are the propellers I cut off and mounted in a new 3D printed hub with a aluminum bracket there. So they are now at around somewhere around the 24 by 24 inch. It's a little bit awkward when you're like changing the pitch of a low pitch propeller to a high pitch propeller. It doesn't really add up with the washout or the twist of the propeller. So, but at the tip there, or like far out, the pitch is the same as the precision made wooden propeller from Fiala. So I hope that I'm somewhere in the vicinity of correct pitch for the first test flight anyway. I can always print new hubs with different added angles, but it's still not an optimal solution, of course. But it's a low-cost way of just trying out the first, doing the first hops with, to see if this structure would take the centrifugal force and other like issues I have with this. Okay, so now I'm just about to actually start the machine for the first time. So this is genuinely the first motorized spin of the machine, and it's a good moment. I mean, this is what I love, being out in the nature and fiddling around with like my latest creation. And it's a beautiful autumn day. It's dead calm and actually quite warm, and it's just so nice being able to do this kind of playful things. And this is all about learning, of course, assembling the machine for the first time, and there will be problems that has to be overcome for sure. And I actually started out with not being able to start the motors at all, because it turned out that the speed controllers, the high voltage opto-coupled speed controllers, needed to have the positive wire to the speed controller connected to a 5-volt source. I didn't know that, so I was just having the signal wire and the ground wire connected, but it didn't work, so it took me a while to figure that out. And now I have seen something a little bit discouraging. And well, in the CAD model it seemed to be sufficient to have like 4, 5, 6 inches of air gap in between the propeller tips. But that's in the CAD model. So in real life it turns out that although I have the bracing strut on the wings, it's still quite flexible outside in the outer part. So I do need to separate the two rotors as much more as I can on this central shaft there. So I will add 4 or 5 inches of clearance in between the propeller tips there. This will probably work for the setup right now for a hover test in like nil wind conditions, but it's super unsatisfactory and just scary. And if I do a hard landing, it might they might strike each other, and then I have spent a lot of money and hours in vain. So I will have to move one of the rotors. I think I'll move the upper rotor apart from the lower rotor. So that's that will take me a little bit of time. And I also discovered that one of the 6 wings servo hasn't been the stroke length of it hasn't been adjusted. So one of the wings like really do some significant pitch movements, and the other ones are restricted to 20 degrees total stroke length. So I think you'll see that a little bit later on here, that one of the wings flaps violently that when I do control inputs. Well, that might not be now. I'm doing the yaw testing first here. And this is the close-up of the system. So it is a Kevlar wire, Kevlar rope there, wrapped around a aluminum cylinder, which is secured to the central part there of the shaft. So that's stationary, and the servo with the rope there is turning around when the machine is spinning. And it is set up in such a way that the rope there is like self-tightening. So I have significant servo assistance, so to speak, of that setup, and the servo actually has to do a very light duty work, just slightly tensioning the rope there, and it will grab the cylindrical part there pretty significantly. And I guesstimate that this system will consume around 0.5 or 1% of the total power. So it's fairly efficient, but I really should have gone with disc brakes, bicycle disc brakes instead. I think I would have even lower power consumption and a more linear torque transfer. But I will try this system out first. So now I'm gently spinning up the rotors, which is difficult because the yaw and the throttle is the same stick, and at 12 cells the motor is very easy to just over control. But you can see here that I'm moving around the yaw stick because I have the movement there of the undercarriage. So I'm transferring torque from either the upper or the lower rotor to the center shaft there, so I can make it go left or right. Yeah, and here I'm just trying out the general controls as well, and you can see one of the wings is really moving too much. So that's the wing with the non-uncalibrated servo. So it's really like pitching like crazy. And right now I have set it up for only 10 degrees of what do you call it, pre-timing. So if I want it to go backwards, the wings will give a high pitch in the front of the machine and vice versa. So I will see if that works out. I think since this is centrifugally cancelling out each other, the rotor, there shouldn't be much phase lag except for the servo movement time. So I have 10 degrees for that at the low rotational speed of 1 to 1.5 revolution per second. But that's all just for future, like for the future to show if I'm way off here, or if I'm if I got the thing under control. So now I'm doing some retensioning here of the Kevlar string and just checking it out. I realized that if I spin up the rotors with the motors to just a random RPM and shut off the power, I can see which rotor has the most dragging brake, so I can adjust them to be dragging pretty equally, because you do need some friction transfer all the time from the rotors to keep the undercarriage there from just randomly turning left or right. But of course you don't want the brakes to be too engaged, because you will lose, you will rob the system from power and generate heat. Yeah, just the random like YouTube thumbnail posing there. Mandatory. Yeah, it's pretty big. It's so mesmerizing to to stand close by an object you built that is this like ridiculously sized, and it will be scary for sure the first time I power it up to try to get it up in a hover. And just some random close-up pictures here. Again, you can see the yeah, that's the collector, what do you call it, the source plate, which transfer the ground and the speed controller and the pitch signals from the flight controllers over to the wings, which are picked up by brushes on each wing, and they connect once you assemble the machine. The brushes intersect there with this wash plate automatically, and there are the massive battery packs on the upper wash plate as well, and the brushes there you can see. Yeah, but again, if this survives the first flight, I will do a more in-depth review of the various parts here. Okay, so setting it up for the first crash. See you in the next one. Bye.